Thank you for all being here. I know it's the height of the holiday season here in the UK, and I took advantage of a trip that I was on to come by and visit, and I'm thrilled to have the chance to talk to you all at the Turing Institute. This is the title of my talk, A New Type of Thinking. It really is a talk about what I did while I was at the Defense Advanced Research Projects Agency at DARPA, some of the programs I helped start. But first, I wanted to give you a little context because I'm no longer a government employee in the United States. I'm back to academia. I got my PhD in 1995 from the University of Maryland at College Park. Spent a little time at the government lab called the National Institute of Standards, a little time at Carnegie Mellon, 17 years at Drexel University, and then I had the privilege of serving the United States Defense Department from 2014 to 2018, really first week of January this year, in the role of Deputy Director and then Acting Director of what was the Defense Science Office at DARPA. The Defense Science Office is DARPA's DARPA. It's where all the amazing, crazy stuff occurs that hopefully later becomes game-changing technology. My personal view of the world, this is sort of my little mantra, is I see myself as a computer scientist who, this is my personal advert here. Computer scientist seeks domain scientists with whom to venture forth and find new computing phenomena. So I'm like a physicist in a way. I don't think anything is out of scope for computer science. I like to look at computing problems in the world, and every problem has some interesting aspect of information, data, and computation in it, and I can find cool stuff to do as a computer scientist. So when I was at DARPA, this became a common theme for me and some of my colleagues across the Defense Science Office, because as we were developing programs at the agency, computing and data analytics, computation, modeling and simulation, these were the tools with which the program managers looking to solve problems were going to change the world. As we realized that over the last 15, 20 years, the amount of data available to us, the amount of computation has transformed what the real problems are. And we developed projects across a whole variety of different disciplines in which computing and data in some form was the central enabler. So social science, we had work in engineering design, human machine systems, mathematical foundations. We actually looked at what the limits were of machine learning and technologies like that. So the establishment of these programs in concert with the program managers was a thrill for me because I got to see science writ large. And the talk that I have here is a talk that I actually gave to the agency as a whole before I left. So this was last summer. And it summarized some observations I had about the way the whole agency was working on problems using data and computation to transform the way they're solved. So, but before I do the talk, I wanted to say a little bit, if you don't know about the University of Maryland, quick advertisement. The University of Maryland is the flagship campus of the state of Maryland. We are in College Park, which is inside the Washington, D.C. Beltway, about 15 minutes from downtown. I am affiliated in the Clark School of Engineering, where the Institute for Systems Research lies, but also computer science, which is in a College of Computing, Math, and Natural Sciences. The computer science department is very well regarded. It's very large. We have a huge undergraduate population, something like 4,000 students, apparently the largest in the country, undergraduate. The College of Engineering spans something like a dozen different departments. And the Institute for Systems Research, which I direct, is the interdisciplinary research center housed in engineering that's meant to bring all the different components from across campus together to solve systems-oriented problems. And the history goes back to 1986. We were one of the initial, what was called engineering research centers from the National Science Foundation, the first year they did it. Just some data about the Institute. It's about 60 faculty affiliated with it. Some have part of their appointment in the Institute. Some are just affiliate faculty. We do a whole variety of activity across the NSF, DARPA, and other agencies. And if you want this info, you can have it, but I just want to give you a sense. It's essentially a place where the interdisciplinary work tries to come together on campus. The core technical areas that the Institute has are communications, networking, micro-nano devices. We have people doing neuromorphic computing, and we have people doing logistics and supply chains and optimization work. And these are the core scientific disciplines in almost any system that you'd want to build today. And it's just some examples from our portfolio, everything from robotics to brain imaging to implantable devices. And some of the places we're going, and this is one of the reasons I wanted to come visit, is learn about where your organization's going. I know you're fairly new, and see if there are ways maybe we can partner and in what areas. So let's get back to this talk. So I got to give this presentation to the agency as a whole, and I treated it as it was a real privilege because not everybody gets to give a talk to all of DARPA, but also on the leadership team I got to see this pattern of discovery. I got to see what the program managers were working on across every different office. And I said to the director, I said, you know, there's a formula here that we're beginning to use over and over again. And the program manager in robotics isn't necessarily talking to the one in data science, isn't necessarily talking to the software engineer, but guess what? You know, the formula for the program is almost exactly the same. So I developed this presentation with the input of many others, and it's entitled A New Type of Thinking. And the title comes from this quote from Albert Einstein in a very famous op-ed that he wrote in 1946 in the post-World War II, then nuclear era, where he said that a new type of thinking is essential if mankind is going to survive and move towards higher levels. And you know, he was pointing out the threat posed by atomic weapons at the time, that the human race is going to have to think differently, otherwise you know, there's going to be a problem. I've come to believe that we're in a similar state of the world right now, where there are technologies that are transforming the way society functions. Many of them are computing and data-driven, and we are at the cusp of developing new types of thinking in order to control, harness, maybe even solve the problems that are coming our way, whether they be climate or health related. So the example that I'll use to drive what I mean by new kind of thinking is from my domain, where I did my bulk of my research when I was a student and then as a faculty member. And that was in automated manufacturing. So let me give you an example of what new type of thinking means, and I'm going to ground it in some examples. So here's the world we're in today, if you're a manufacturing person, right? We can 3D print things, right, of amazing complexity, like these lattice structures. This is an ultralight metal part that some DARPA performers at Hughes Research Labs in California had produced. You know, amazing, right? It sits on top of a daffodil. These are metamaterials that can bend light in different ways. This is something that some colleagues did at this model here, this polymer and aluminum oxide. It's a hybrid material that is thermodynamically stable. So instead of having a refrigerant, complex mechanism, you can actually have a part that does this work of maintaining stability, say, for a device that needs to be really stable. So this is the world of manufacturing today, is all these complex things you can make, right? And there's a huge combinatorial problem when I try and manufacture something, which I have all these new possibilities where literally, and this example here is showing how if I change the energy deposition, if I change the level of energy in an E-beam or laser, I can actually change the material property of a powder. So the metal powder is the same, but because of the energy deposition, I get these different grain structures that lead to different performance parameters. So suddenly I'm in a world where I'm literally controlling millimeter by millimeter the amount of energy I put into a thing I 3D print. So I've gone from, you know, making something on a lathe to now almost every micron I can control. So the number of possibilities have exploded. This is the way manufacturing works today. But this is the way traditional design functions. We're still based on essentially measurements and dimensions, right? When you sit in front of a CAD system, what do you do? Well, you draw the part, right? You draw it this length, and I'm going to make it out of metal. So this is a 200-year-old process, right, developed by the armories in Harpers Ferry and Springfield, Massachusetts, in order to standardize rifles that the US military realized in the War of 1812. Rifles were made by gunsmiths, right? So your rifle and your rifle, you couldn't, I mean, the parts looked the same, but they weren't standardized, right? So over 20 years, the military invested in the development of standardized parts, which meant there was an external representation of information that they had to create in the form of jigs and fixtures that would describe then the parameters of the parts. Then that let us essentially build something more complex. So these examples here that I have are actually, it's a historic timeline of innovations in human technology that have helped us manufacture things of increased complexity. All right, so remember I'm talking about new type of thinking, right? So human brains have a certain limit, and what we do is build technology to help magnify or amplify what our brains can do, right? So one of the first technologies human beings figured out was writing. Turns out this tablet is one of the oldest examples of ancient Sumerian cuneiform, and it's the ingredients to make beer, because that was what we wanted to make in order to have, essentially something to drink, because we couldn't drink water. So think about it, manufacturing. That was the reason I started, one of the principal uses of writing was to log food crops, in particular make beer. Thumbs up, okay. So fast forward a little bit, another example I like to talk about is, all right, so I know how to make a ship, I go to a shipwright. Well, what the Venetians did in the 11th century was they figured out that shipbuilding could be broken up into a supply chain and we could have specializations of labor, right? So they built an organizational structure that was embodied in what they called the arsenale, which was the factory. If you go to Venice, you can see this, right? It's actually a Navy base now. Apparently, you can kind of look in, but if you look at this famous painting, it actually shows the manufacture of ships where they divided up the labor into the folks who did the rigging, the folks who did the weapons, folks who did the planks, and they could literally pound out a ship in a day because they had an assembly line. Little, assumption is, oh, Henry Ford invented the assembly line. No, the Venetians invented the assembly line, right? And that was their strategic advantage, that shipbuilding was now about an organizational structure of human beings working to produce templates for the parts and then the ships. And then eventually, we go from 1812 with standardized parts to now things are represented mathematically, right? So if I go to a CAD system, I draw dimensions. But in reality, these mathematical data structures underneath our computer graphics systems are essentially approximating the templates. So think about this again as human thinking, human being endeavor to make artifacts, right? So there's some cognitive limit of individual human beings. I mean, we get more educated, right? And we might have greater capacity than previous generations in terms of the knowledge available to us, thanks to Wikipedia and our smartphones. But at the end of the day, our brains are limited. So we build tools to amplify what our brains can do, right? The accountant has a spreadsheet. Well, Excel is more powerful than a physical spreadsheet, right? But Excel is just a tool. So writing is a tool, the assembly line is a tool, the interchangeable parts is a tool. We've created a set of tools that amplify what we can create, but at the end of the day, the process of creation is still what our human brains we're always doing, right? It's not that different, akin to, say, digging a hole, right? You can dig a hole with your hands, you can dig a hole with a shovel, or you can have a backhoe and a steam engine. At the end of the day, you're still digging a hole. So very much the tasking has remained largely the same, but our tools have given us increasing sophistication in what we can produce and design, right? So this is where we are today, is I have these fast, super advanced manufacturing processes, and what do I do with them? Turns out I do what I was doing before. So here's an example of a part in Inconel 718, and it's some kind of housing, and great, it's made as a brazed casting, machined finished parts, etc. And I have now these awesome 3D printers, and what am I doing with the 3D printers? I'm trying to make sure the 3D printer can print the metal to match what it was before. It's like, wait a second, it's the same thing, right? I've not taken advantage of any of the new possibilities because what I'm doing is what I did before. One of the best examples, which is not to be in any way disparaged, this is a fantastic example of 3D printing, was General Electric over several years invested significant amounts of energy to redesign this critical part in their jet engines. This was the fuel nozzle in a jet aircraft engine. And there's something like 48 of these around the perimeter of a jet engine, and it was originally 21 parts. It was a pretty complex artifact, and it would be prone to failure. There's places where it's brittle, it's got to be welded. So what they realized is they could basically make all that in one go on a 3D printer. And they spent a significant amount of energy, time, money to redesign the part to make it on a 3D printer, and huge difference in the LEAP engine, huge increases in reliability and efficiency, but it's still largely the same thing, right? It's like we might have taken a leap forward due to the technology, but our feet are still firmly planted in the way the world was before. So what do we mean by a new type of thinking? So what we were seeing at DARPA, my colleague Jan Vandenbrand and I, Jan was the program manager who came up with this idea, was that there was this inkling of like, maybe we could change it, right? Maybe we could change the way machines and humans create things. And he was looking at this problem of topology optimization, where you simply provide the physics parameters to the computer, and the computer then synthesizes a shape. So you're not going in and drawing dimensions. You're saying, I need this kind of heat dissipation. I need it to hold this kind of load. Tell me what you got. And the computer then synthesizes a shape. So this is an image from one of his performers of a heat transfer device where there's some airflow that comes in, and there's some airflow that comes out, and suddenly there are these heat absorbing surfaces along the way, and it holds some kind of load. And if you look at it, it's organic. It looks like some, I mean, no human being would draw these shapes, right? It's like an organism, not a set of straight lines. So you begin to wonder, well, okay, how's this come about? And it's, the machine understands physics. The machine understands some input from the human, and the machine is essentially generating the moves. But the moves, if you will, the configuration on the board, is not something that I as a human have ever seen, because it's alien to me. So you begin to see this notion that there might be some way we can use the machines better to augment our thinking. So the thesis is that we can algorithmically augment human thinking. Three key ideas. The first idea is, well, I need to change my relationship with data. So I think this is widely accepted, that data is important. If you do machine learning, analytics, et cetera, people know that data is essentially the fuel, the raw material in which I can feed the engine of a machine learning algorithm. But it's more than that. I got to change the relationship with data, because in certain disciplines, data is viewed as the byproduct of the work, right? The goal is to create the artifact. The data is just, that's what I do on the way to making the artifact. The data is the main artifact. The thing I 3D print into the world is a projection of the data, right? The world and the data are interchangeable. I have to think of the data as the principal artifact increasingly. So this is what I mean by change the relationship with data. Second thing is, computing, we've begun to view it as a limitless resource compared to what I had before, right? I mean, I grew up, I'm just old enough to, you know, remember my summer job where I had to do installations on IBM PCs, you know, floppy drives, and putting whatever it was, Windows 2, or no, Windows, I mean, it was DOS, like 2.0, right? I remember putting the memory board in, you know, adding another 120K, right? You know, now it's to the point where the amount of computing power I have in my phone, you know, dwarfs what the entire Allied armies had during World War II, right? So, you know, computing has become a limitless resource, right? But most of our conceptions of computing is limited to what we experience on desktop, right? The fact that I can get unlimited, not unlimited, but let's say, for all intents and purposes, compared to what I'm used to, unlimited amounts of computation via Amazon Web Services or other commercial services. You know, we haven't figured out how to quite tap into that yet. And once I put a little machine learning in there, suddenly these computing cycles can be used to find patterns in ways I didn't know I could before. The third piece is, okay, if I have data as the fuel and computing as the engine, with machine learning as maybe a piece of this algorithm, the issue is the machine's going to come up with patterns that then I'm not going to be familiar with, because it's going to see the world in a fundamentally different way. So I need to find ways to alter my senses, because the results of the 1 and 2 are not going to look like anything I've seen before. So think of it as the chess playing example. I'm going to see moves and patterns that don't look like any move or pattern that a human being's ever made. So this is what I mean by creating a new type of thinking. We're going to go from machines as tools, where cognitively, if I'm using a tool, I still understand the problem, right? The shovel, I get it. The backhoe, I get it. It's the same problem cognitively. But if I go to machine as partner, then suddenly the machine and I, nobody has the full picture anymore, right? Just like if you're doing interdisciplinary work with another human being, you know, I'm not an expert in virology, and the virologist isn't necessarily an expert in computer science, but the two of us could then somehow work together to solve a problem in, you know, epidemiology, right? They don't understand my world. I don't fully understand theirs, but somewhere there's an intersection that we can work together to do something that's more than either of us could do alone. So in that case, that's a partnership where the space of opportunities we're looking at is somehow very different than if it's just as a tool, right? So let's do a couple examples on each of these. and then we can have a little discussion. So the first about changing the relationship with data. So today, data is viewed as a curated artifact, the byproduct of the work, right? It's not the thing. What's new is that data is this raw material, and I need to manage it in such a way so I have it there to feed into the machine that I'm going to use to find order and patterns in it. One observation is most data we're never going to touch, right? Because as the world produces more and more data, the amount that human beings is going to touch directly is essentially going to zero over time, 0%. So the machines are the only way we're going to get access to the data. Another observation here is that the ecosystem of software tools for extracting meaning and value of data is exploding exponentially, getting much, much better, right? Once you put your challenge out on Kaggle, the Kagglers come and they figure out the data pipeline, and guess what? Once you have it, you can use it over and over again, right? So this notion that we stand on the shoulders of giants is compounded in the software arena, because once you figure out how to get a file from format A to format B, I mean, you're done for good, right? I mean, anybody can then do that, right? So the bag of tricks that we're producing is getting better and better and better all the time. And what this lets us do, if we're bold enough, is we can shift the economics of handling data onto the people who eventually want to use it in the future as opposed to the people who create it now. So this is a pretty radical idea in some circles, because data is often viewed as a curated artifact where I've put the right metadata on it and I've labeled it. And what we're saying here is actually, no, you don't need to do any of that. just give me a bucket of data. The tools are getting so good that I'll be able to make sense of it anyway, or at least adequate sense of it anyway. The issue is that the human beings don't have time to organize it, because there's too much of it. So the best I'm going to be able to do is keep as much of it as I can with as little effort as possible, and then let the tools find the patterns later. So the key insight here is that consider keeping as much data as we can reasonably, curate forensically. So forensically meaning like crime scene investigators, right? You're going to go and figure out what happened, right? So curation isn't going to be up front, it's going to be forensic. It's going to be down the road. 5 years from now when somebody wants it, they'll figure it out. And then if we're going to do that, then what we have to do is accept uncertainty in the data, because it's not going to be well labeled. It's going to be missing stuff. But the good news is that you'll be at least open to what the future uses are, which may be very different than what you think of today, right? Because if you start filtering the data today based on how you think it's going to be used, you shut the doors for a whole bunch of opportunities in the future, which you can't imagine what somebody's going to want to use it for. So we did an experiment under my tenure at the Defense Science Office, where we took data from one of our programs called Open Manufacturing, and we got an outside party, not involved in the program, to curate it. And we basically, this isn't big data. I mean, it's a few hundred gigabytes, but it is deeply technical. It was structured, but uniquely structured for each of the performers. And we gave the folks at Rensselaer Polytechnic Institute, who were the performers on this test, we gave them no access to the original producers. We just literally gave them hard drives. We said, figure it out, tell us what's there. Organize it however you see fit. So the group at Rensselaer included a material scientist as well as some data analytics people, and they basically took their tools from that data ecosystem and they figured it out. They went in and they figured out what photographs went with what experiments. They figured out what documents described what manufacturing plans. They even found some data from tables that came out of the experiments, because what this program was doing in this example was doing materials testing, so trying to correlate material performance parameters to the manufacturing parameters. So if you wanted certain material parameters, you knew what the manufacturing parameters were. So what they were able to do is calculate areas of expected performance in places where there were no experiments, because they were able to do a little machine learning and then say, oh, then, if you want these performance parameters, here should be the manufacturing parameters. So suddenly now you're deriving new work from this data. If I had given the task to the performers as to what data to keep, the answer I got from one of them was, well, we have all the data. We keep it all. And I said, well, what do you keep? And they said, oh, we have a spreadsheet. I'm like, spreadsheet? But you're doing like CT scans of the data. You're doing this. Oh, no, we don't keep that. We just keep the spreadsheet. I mean, they were literally just keeping the final parameters. And you're like, well, first of all, if I need to reproduce the science, I probably need the original parameters. But second of all, I mean the original data. But second of all, I want to discover anything new. I couldn't do that from just the spreadsheet. I needed to have this stuff, right? And who knows, the use might have been for some image processing project where people wanted to look at like visual inspection of parts or something, right? So what we learned here is that guess what? You know what? You just keep everything and let the tools organize it later. If you have a motivated data consumer, they will figure out something there of value. Right? That was the first observation. Okay, second observation, computing is limitless and more or less free. Computation is this machine for finding order in this vast swath of data. And I have currently unfathomable quantities, available. So this is an example from about a decade ago from Hod Lipson, who was also a DARPA performer, not for this project, but on some of our current work. Hod is currently at Columbia University, and he's well known for some of his work in evolutionary design and mechanical engineering. In this work, which published in, I think, Science, he discovers the equations for a double pendulum simply by watching a double pendulum. And this is because he seeds the algorithm with a few hints of the kind of math, and it has plenty of cycles, and it just watches and eventually figures out what the set of equations are that fits to what the phenomena are, right? Now, it's not totally from scratch, right? It's not discovered the laws from scratch, but it's with a little bit of human intuition here, it's found some patterns that are pretty profound, right? So think of it this way. I've been heavily influenced by a book, which I recommend. I read this book about a decade ago called The Origin of Wealth by Eric Beinhocker. This was written in 2006. Think of this as an entropy problem, right? I'm trying to find a reduced order representation for something I see in the world. The machine can do a lot of work for me for free, right? So what happens is I take human attention, specify some equations, some hints. I take energy and a computer, right, essentially electricity, the computing device. I give the computing device an algorithm and some data, and out comes essentially stuff of value. So what Beinhocker would say in Origin of Wealth is that stuff of value amounts to objects of decreased entropy that somehow provide me a utility that I didn't have before, right? So here comes out of the machine some kind of insight, which then I can use. Maybe I make a product, maybe I make a scientific discovery, I don't know. But here's the equation where energy, okay, that we're understanding that if you're a Bitcoin miner, we're using up a lot of energy, but human attention plus energy plus computer, suddenly algorithm data, I can produce stuff of value, unexpected stuff of value. All right, third observation is about altering your senses. And this is probably the most squishy of the 3 points, right, in this formula for changing the way we do discovery. So I just have examples here of altering senses, and I'm just going to, it's an intuitive concept, but let's see if we can point at it. Here's some work done well over a decade ago by Louis Vanon at Carnegie Mellon called the ESP game, where this was a collaborative online game where you and an unknown partner had to guess a label for the image. And basically, over the course of many months, he was able to label almost every image on the internet at that time by having people play this game, right? Because he made a game where your input into the game was doing this collective computation, where part of the computation was done by the machine, part was done by the human. So your view into the problem was different. He altered your senses and then suddenly is doing a big problem here of the sort that we wouldn't have done before. This is the view of move, I think it's move 37 for AlphaGo. If you've not seen the video of this, it's pretty awesome, especially if you watch the one with the commentary where you essentially have two, sports reporters who do Go commentary, which is interesting. I didn't know that existed. But so watch this. This is a video. This is move, like I said, 37, where AlphaGo decides to put a black chip, a black stone right here. And the machine produces the move, and the guy who's placing the stone moves it over down here, and the other guy goes, no, it's up here. And the guy goes, no, the computer would never go up there. And it's like, oh, it went up there. Flummoxed. The reporters are flummoxed. And then what happens is, a minute later, Lee Sodal gets up and walks out of the room. And the coverage in Wired is fantastic. So there's a summary of this story in Wired magazine where he's interviewed afterwards as to, well, why'd you leave? Why'd you quit? And he realized the computer was playing a different game. is that his understanding of Go, which was the best in the world, was lacking. The machine saw something different. And now with AlphaGo 0, what has emerged is that the patterns the machine sees create attack surfaces, if you will, within the game that are much more complex and subtle than a human brain would have thought of on their own. So what this ultimately ended up being is that the machine was actually doing what looked like a weak move was actually part of a strategy of a lot of weak moves that collectively were too complicated to counter, right? And that's sort of the knowledge of my Go, so we'll just stop there. But you know, here again, perception of the world is being altered by the machines. The example I really like to give is this one that's a crowdsourced scientific discovery example from my colleague Jim Hendler. Jim is at the Rensselaer Polytechnic Institute. He was the program manager at DARPA in the early the early 2000s, late 1990s. And he was responsible for the program that became the DARPA agent markup language and what is now known as the semantic web. Sir Tim Berners-Lee was funded under this program, so a lot of this semantic science Jim laid the groundwork for. So Jim gives this example of this Dutch woman who was part of a thing called Galaxy Zoo, which was using the Sloan Digital Sky Survey to look at images. And the Sloan Digital Sky Survey was a product of the work of Alex Zalé at Johns Hopkins and the late Jim Gray then at Microsoft, where they basically turned astronomy into a data science. Prior to Alex and Jim Gray, the perception is, well, astronomers, you need a telescope, right? And if I have a telescope and you have a telescope, well, you know, I don't want to show you my telescope, right? This is my observations, my time. What Sloan did is let you aggregate observations by creating a data infrastructure where I could share my observations. Okay, so initially, astronomers hated it. And then they said, oh, okay, I can get yours. That's all right. We share alike. That's good. So that was sort of the first wave. But then the second wave adoption came when they realized that the nature of astronomical inquiry has changed to be about queries on the data. So it's no longer about making a specific observation. It was about making some kind of data-driven inquiry across the corpus that's now in this survey. So here's Hanni van der Moort, right? If I pronounced her name correctly, incorrectly, I apologize. She discovered this quasar ionization echo phenomena through Galaxy Zoo, which was essentially a crowdsourced way to label the data in Sloan, where the interesting images were identified computationally and then farmed out to human observers to essentially label. So this green echo was something she found, and here's the paper that involves her and Alex Zalé and others, you know, documenting this new phenomena. So suddenly we're making scientific discoveries by taking human attention, altering it, having the machine focus it, and then in this human-machine system, you know, creating some new discovery. Turns out I did stuff like this in the past too. So this is one of the benefits of being kind of mid-career, is you can look back at what you did before and say, yeah, I did that too. I worked in design and manufacturing, and one of the areas I worked in was 3D search. So think of that problem of, if you're a designer sitting in front of a CAD system, the way the CAD system works is you draw dimensions, draw the part. It's like, it'd be much better to sketch the part and do a search and bring me back stuff that's like what I want to make. Well, you know, that was what I was working on for about 10 or 15 years of my career, were search algorithms where you could go and say, hey, I need a bracket and I need it to be a machined part. I'm going to make it on this kind of machine. Can you find me that kind of part in a database, right? So searching based on things like function, behavior, et cetera, rather than on merely you know, dimensions was work I did. So all part of this transformation to having the machine do more of the work, changing the role of the human in the system. So let's bring this home. Here's the axes I showed before, right? I have machines as tools. I have human cognitive capacity. I've sort of flattened this out, so imagine this on the plane. So human beings, individually, we have some boundary, right? And what kinds of problems we can solve. In groups, we could argue that that boundary actually decreases, but let's, you know, could be, let's just say it's not a linear relationship, right, between the capacity of a group and, you know, it isn't a factor of 10 of the individuals, right? So you've got this system, which we've been around for years, and what I want to do is actually get up out of the plane. So the thesis is, the observation we're trying to make in this talk is that there's actually this other dimension where machines as partners is really a symbiotic system where the human and machine partnership leads to something more than just the machine being my tool. And I can get up out of the plane, and I might be in some spot like the Sloan Digital Sky Survey, where suddenly I'm doing science at a whole other scale, or inquiry in a radically different way than I would have if I was just a bunch of human beings with my computers as tools. We ask questions about, okay, if I do this, what's the real problem? Where are the long poles in the tent for this problem? So one thesis is that, and this goes back to Jim Gray, this is from his Turing Award lecture in '98, that it's really about human attention and how to focus it. So I have these silicon devices that are really good at a certain kind of pattern solving, and I have the human brain, which is good with a certain other kind of problem solving, and I want to put the two of them together. Ultimately, this might mean, how do I best allocate human attention in this environment where most information is stuff I'm never going to see? So machine as tool just magnifies the senses that I have. As partner, it means I alter my senses, and it means I focus human attention in a different way. The message I gave when I presented this talk at DARPA is actually this is something that the agency had been working on for 40 years, 50 years, right, since the founding of the agency. This is J.C.R. Licklider, who was at DARPA in the 1960s, was a famous acolyte of Vannevar Bush, and he authored a paper entitled The Man-Machine Symbiosis, which is a prescient paper for 1962. Among the people that were funded by the early work at DARPA was somebody named Doug Engelbart, who was at SRI at the time, and he's the one responsible for the human-machine interface that was born at SRI, later implemented by a couple ex-DARPA people at Xerox PARC as part of the Alto, and then by every story used as inspiration by Steve Jobs when he eventually had the Lisa, right? So the roots of this narrative, we see in our iDevices all the time. Just understand that within the context of problem solving, there was actually a pattern here. Engelbart didn't do this as an open scientific discovery problem. He was actually trying to accelerate human programmer productivity. That's why the emphasis was on editing, collaboration, the hypertext and the interface was all about essentially building programmers' tools to amplify programmers. And in this report from 1962, there's this marvelously anachronistic flowchart with some really quaint language from the 1960s about how to do this. It's a machine for making augmenting frameworks for the human intellect. And then if you boil it down, it essentially amounts to doing foundational research, finding these components, finding real-world problems that can be solved, and then aligning the components against the problems to transform our perception to then build these tools for augmentation in different capacities. So to summarize, where I think some of the current opportunities are for organizations like your institute, but I think computer science and engineering as a whole, is we're looking at ways, how do you alter your senses in these environments? What are the most effective ways? This is more than just human-computer interaction. It's about joint problem solving in some way with a machine. How do I unleash computing and data? How do I make this software toolbox easier and easier to use? And then where there are applications in mind, the people with those applications are probably not the computing people. So you need to kind of work across the disciplinary boundaries to redesign the problem, the process, and the people involved so that you can really use the computation as a means of altering problem solving. One way we viewed this at DARPA was, if you know kind of the standard knowledge management hierarchy, data, information, knowledge, understanding, wisdom, right? There's data is what our sensors pick up, right? We pick up sensor data. Turning that into information requires some kind of filtering or rarefication, right? And for the most part, until 70 or so years ago, this was done by human beings, right? So think of it this way. The Babylonians had star charts. Somebody like Kepler and Tycho Brahe organized the star charts in a way that Kepler was able to produce his laws of planetary motion, which describe very succinctly the motions of the planets. So the Babylonians had the data. So if you were like a big data person in ancient Babylon, you'd just have these correlative tables that say, well, the red one moves this way and the other one moves this way, and these 6 of them move in a funny, but these other ones, right? You would just be down here and you'd be perfectly happy because you've defined it all with data. But Kepler reduced it all to a set of equations, right? So if you think of this hierarchy as an abstraction hierarchy, the role of the machines is to amplify our capacity up this hierarchy. So I'm going to jump a couple slides ahead. I'm going to jump to this one here, yeah. And then I'll pop back. So this is a very busy slide, but the way to think of it is, there's the world. The world's out here. Human beings are on one side. Machines are on the other side. The human beings have to deal with the world through their senses, and then we try to organize knowledge and essentially to survive. And we produce these abstractions, these tools, et cetera, that help us societally, help us individually up this food chain from data, information, knowledge, and wisdom. The machines experience the world through sensors, and then there's algorithms in here, and AI, and user interface techniques. So what the machines are doing is helping us understand the world, and somewhere on the interface is this boundary between humans and machines, and we can begin to look at many of these interesting societal problems, like understanding the behavior of an urban environment and how to better optimize the care of a city, how to understand climate phenomena, et cetera, as essentially an effort to take the machines and augment our senses. And somewhere between the machines and us, we have to have a dialogue to solve the problems. And it's about designing what these interfaces are and about building the scaffolding on the other side to get the machines to help us have the insight that we need to have. What I did at DARPA, I'll just highlight a couple things, because we found this in a whole bunch of programs we were doing. So we'll do this one. So Make It was a program started by a colleague, Tyler McQuaid. He was a chemist. And he had this insight that, chemical reaction planning was a human job. It's literally the beakers and the test tubes, and trying to figure out how to go from these things that you had in the lab to something like a ibuprofen on the other side. And there were people designing things like microreactors and plug-and-play chemistry sets, where he realized that, well, I kind of got a compiler that could do the reactions. What I need to have is a way to do the programming of the chemical reaction sequences. And he set up a program called Make It, which looked at these reaction sequences and tried to encode them as information products, sort of like a plan in AI, preconditions, postconditions. And then what happens is you can build tools that augment the ability of chemists to do reaction planning, right? So in this case, they actually built tools that had, I think, undergraduate or graduate student chemists doing reaction sequences that were at a complexity that really only an experienced postdoc would be able to do. So cognitive amplification, right there. I gave somebody 5 years of education simply by giving them the right tool. Right? The one that Jan van der Brand developed was this program called TRADES, which was transformative design. And his goal was to make computers symbiotic partners with humans so that they could come in, a human being could come in and specify performance or behavioral parameters and have the machines synthesize designs that might span multiple scales or orders of magnitude. So I could make use of some of these properties that a 3D printer could achieve. But the human brain, too many options. Like I'm trying to design a heat exchanger. I mean, I can't possibly conceive of something across 4 orders of magnitude of scale. So this project is still ongoing. There was another one. So I got chemistry, I got manufacturing. There was another one that a colleague of mine, Lytton Salmon, did in MTO, which was looking at a similar design problem, but in the context of the design of electronic circuits, where again, there was a data problem. The idea was, could I put things in a repository and use the repository to drive acceleration of design patterns? There was another colleague, this was Paul Cohen, in the Information Innovation Office. His insight was, I could do accelerated scientific discovery if I could have computers read technical papers. So this became a natural language and machine reading problem. He used cancer research as the domain of study, and what he had was algorithms that would read papers in PubMed, which is the big medical library in the US, understand the text, the experiments, maybe the figures, maybe the diagrams. And then these papers would build computationally a big mechanism for the action of the RAS genes in certain cancers, so that a clinician or a medical researcher could better design an intervention or a treatment or a study. So suddenly the computer is your partner, your lab partner, and it has an understanding of the paper. Not the same as you would as a human, but you can't possibly read 20,000 papers. So what's the choice? You literally at the kickoff meeting for this project, one of his performers got up, who was a medical scientist, and he basically said that his work is stuck. He can't go any further without the machine as the mechanism to accelerate discovery. So I conclude with this image of the Detroit Institute of Arts on the wall. This was something we wrestled with in my time at DARPA. Is like, how do we talk about human-machine symbiosis? Like, is there a picture? And the best I could do is do it by analogy. This painting was done by Diego Rivera, a famous artist of the 1930s, and it was a celebration of human and machine labor working together to build the cars in Ford's River Rouge plant, right? So from the raw material coming in to the engine blocks going out, humans and machines partner together in physical labor. So really what we're talking about is, in this transformation, cognitive labor and getting us to work together cognitively. I put out some open questions, the most, I don't know, disturbing of which are things like, can machines innovate? What's computation even mean? Does it come down to human attention? Is that the best metric? Are there other metrics? Are there any principles for shifting complexity to a human-machine team so we can build better partnerships? As machines do more, what's left for humans? So this does get at some of these fundamental questions people are talking about with AI. But I mean, the good news is that here's a framework for trying to emphasize what the humans are good at, right? So I have these two images from modern times. This is the one of Charlie Chaplin stuck in the machine that everybody probably knows. The one that's maybe more apt in this human-machine partnership is this one where the owner of the factory decides to try out this new device for feeding his workers so they never have to leave their spot, right? So in this case, Chaplin's little tramp has been reduced to basically working while he's being fed, and of course all hilarity ensues as he tries to keep up with the corn on the cob and the other stuff that gets fed to him. So what I worry about is as the humans and machines work together, we don't want this, right? We want a true partnership, not us to be programmed by the machines. So those are just some observations about what I did while I was at DARPA, some of the programs we created, some of this pattern of discovery, and I'm happy to take questions. So, yeah.